Hello. Can you hear me well? Good. Right. So it turns out that David Vaccaro is going to do math webinars, but he's not available today. So today is going to be physics again, and next 2 weeks is going to be maths. Okay. So and you have three more weeks to do the assignments. So hopefully that's okay. So today we continue talking about circuits. I've got some nice problems prepared for you today, and let's get to it. So it's a mixture of problems. Some of them are hard, some of them are easy, and they're not in order of increasing difficulty. Okay, so let's start with a nice question. I'd say it's quite an unusual question, so let's have a look. Two identical voltmeters and ammeters are connected as follows. Ammeter A1 reads 100, ammeter reads 99, voltmeter V1 reads 10 volts. Now, a really good GCSE student would say, what would a good GCSE student say when they saw this circuit? What's unusual about this circuit? Yeah, the voltmeter, that's not how you put the voltmeter. Nor this is how you connect an ammeter. And also, well, you don't really do circuits with only ammeters and voltmeters. So there's so many things that are wrong with this composition. We are used to assume that ammeter is some kind of magical device that measures current without affecting the current. So basically, putting an ammeter doesn't change anything. That's what you're used to, and in most cases it is true. If sorry, something is just give me a moment. Right. You're used to perfect ammeters and perfect voltmeters and perfect ammeters. These are not perfect voltmeters, and ammeters. What does it mean? Well, voltmeters are not perfect means that they do not have infinite resistance. So the resistance of the voltmeter is not infinity, and the resistance of the ammeter is not 0. But it helps that they are identical. So the voltmeters are identical, and so what we need to do is something we're not used to, is think of a voltmeter as a resistor, and think of the ammeter as also a resistor. And then everything becomes quite easy. So the ammeter A1 reads 100 milliamps. So there's 100 milliamps of current flowing here, or microamps, sorry. A2 reads 99 microamps. And here we must have 1 microamp. Voltmeter V1 reads 10 volts, so 10 volts. So the resistance of voltmeter, resistance of the voltmeter is equal to the voltage on the voltmeter divided by the current. So that means it is 10 volts divided by 100 microamps. So the 0.1 mega ohm. Correct me if I'm wrong. It does seem like 0.1, and then it's mega ohms. Yeah. That's the resistance of the voltmeter. And we need to find the reading on V2. So the voltage on V2 is current 2 multiplied by R, resistance on the voltmeter, which is current I2, which is what? Which is 1 microamp, multiplied by the resistance, so 0.1 mega ohm. And the answer is 0.1 volt. And that's it. It's quite an elegant, it's not a difficult problem. The difficulty is in actually understanding that ammeters and voltmeters, well, they do behave like resistors if they're not perfect ammeters and voltmeters. Okay, so any questions here? By the way, do you know how a voltmeter works? Yes or no? Do you know how a voltmeter and an ammeter work? Okay. Roughly. Yeah. So let's take a coil. So this is an axis. Mega ohm. 1 mega ohm. 1 mega ohm. Now 10 divided by, double check, but no, I don't think so. So 10 divided by 100 times 10 to the minus 6 is 100,000. So 0.1 mega ohm. No, it is correct. All right. So to understand how an ammeter works, so you all see these ammeters, analog ammeter. Okay. So let's say this is an ammeter. You have the arrow. You have the arrow, which is connected to an axis, which is on an axis. I should change the color. Right. Which is on an axis. Now, usually it's either here or here we have a spring. For simplicity, let's make a spring here. So here you have a spring. Oh, no, the wrong way around. Here you have a spring. that pulls it back, basically. Okay, so here it pulls it back. On the other side, connected to the arrow, we have another mechanism. So it has an iron. It has an iron bar. So this is an iron. I don't know the proper name for it. It's a piece of iron thing. Okay. And here we have a coil. We have a coil of wires. So current flows into here. It flows around the coil, and the coil becomes an electromagnet. And because it becomes an electromagnet, it attracts the iron bar into the magnet. And the arrow turns when the current increases, when current flows, when current flows, the iron bar is attracted towards the electromagnet, the coil. The stronger the current, the more it is attracted. The stronger the current, the stronger the current. Attracted. The spring returns the arrow back. Do you understand now? Do you understand how it works? Okay, this is the analog. So basically, fundamentally speaking, current has two main effects. Two main effects of current. Two main effects of current. First is the heating effect. And two is the magnetic effect. So how do you register the current? When you register the effect of the current. Now, building an ammeter that measures the heating effect is not a good idea, because then you have a lot of energy dissipated in the ammeter. It's going to heat up a lot. You are not trying to build a heater, you're trying to build an ammeter. You want as little interference as possible. So it turns out that the magnetic effect of current is easier to measure without affecting the current itself. However, the coil means it is a coil made of wires, and wires have resistance. Therefore, the ammeter will always have some sort of resistance. Okay, we don't have perfect ammeters. The voltmeter is exactly the same thing, except the coil is less strong, and there's a resistor involved. So with a voltmeter, it's the same thing, but you just have a large resistor here that prevents large current. That's why ammeters and voltmeters are sometimes called galvanometers, because they are the same thing. It's just one has a resistor inside. If adding a large, well, not large, but yes, resistor turns it into a voltmeter. So you'll need a weaker spring or something. Yeah. So obviously the current, if you add a resistor in series with the coil, let's say you add a 10 mega ohm resistor, that makes the current very, very, very small. So the arrow has to be much more sensitive for a voltmeter. Therefore, the spring, you would use a weaker spring, the weaker returning spring. Otherwise, you just won't register any current. So voltmeters are also ammeters. They measure very small currents. Voltmeters measure current as well. That's quite interesting that a voltmeter is fundamentally the same thing as the ammeter, just with a resistor added. Okay, moving on. Problem 2. This involves internal resistance. The battery in the diagram, which is a part of an unknown circuit, has EMF 4 volts. Reading on the voltmeter is 6 volts. Find the rate at which heat is dissipated by the battery. The battery in the diagram, it is 6 volts. Find the rate at which heat is dissipated by the battery. Okay. So we have this and this. Sorry, I need to double check something. Seems a bit weird. Apologies. Oh, yeah, that makes perfect sense. Sorry. Of course. So there's a current flowing. We assume that the voltmeter is perfect, and there's a current flowing through the battery. The battery has an internal resistance, so there's a resistor here. A resistor here. So here's plus. This is minus. So the current. We want to know what the current is, first of all, and we write down the equation. We write down the equation that the EMF of the battery is equal to the the voltage, the terminal potential difference across the battery is equal to the EMF of the battery minus the energy lost in the battery. Okay, so the voltage that you actually measure, Do you all understand this equation? So the voltage that you measured across the battery is the EMF of the battery minus the energy lost in the, this is the lost volts in the internal resistance of the battery. All right, so let's just apply this formula. Apply this formula. And why am I drawing the current that way? Whereas clearly the current is flowing the other way. So the current is flowing this way. Current is flowing this way as it should, from plus to minus. So the terminal potential difference is 6 volts. EMF minus IR. So that's 6 equals EMF, which is 4, minus current times the internal resistance. All right, yes, that was missing. R is 1 ohm. The internal resistance is 1 ohm. Okay, so that is 6 equals 4 minus I times 1. And you can see that I is equal to minus 2. What does this minus 2 tell you? What does the fact that the current is minus 2 telling you? Yeah, current is flowing in the opposite direction. Current is, I mean, the battery is trying to push the current to the right, but it's not successful. So that means that the current is in the opposite direction. So current is 2 amps in this direction. So what is the power rate at which heat is dissipated by the battery? So the power is equal to I squared R. And so that's 2 squared multiplied by 1 by the internal resistance of the battery, which is 4 watts. So it's 4 joules per second of heat produced. Okay. Problem 3. Find the current that is flowing through the perfect diode in the diagram. So we've started this problem last week. I just wanted to go through this to the end. Find the current that is flowing through the diode. So there are 2 scenarios possible here. First, so let's label the potential here phi 1 and potential here phi 2. If phi 1 is, well, it can't be. Sorry, that's very incorrect saying that. Basically, if the current is trying to flow to the right, there will be no resistance. And if current flows right, yeah, phi 1 is equal to phi 2. the potential has to be the same because the diode has zero resistance. So effectively, if you have like this, sorry, and the current is allowed to flow from phi 1 to phi 2. But in this case, they have to be equal because along a wire, the potential does not change. So here we have 100 volts. Here we have 0 volts because that's the ground. Ground is also always 0 volts. Current will just simply flow here. If current tries to flow left, then phi 2 is greater than phi 1, and the diode closes. So effectively, you have this situation. You have the situation is equivalent to this. This is 0 volts, this is 100 volts, and you have nothing in between. So the diode is just like an open switch, and an open switch is equivalent to not having any wire at all. So what we need to do is we need to do calculations in both circuits and figure out which case is it. So case 1. So this is 1 kilo ohm, 1 kilo ohm, that's 2 kilo ohms, that's 3 kilo ohms, and that's 4 kilo ohms. And so that's 1K, 2K, 3K, and 4K. Well, let's calculate the second circuit first because it's easier. So let's call this phi 0, phi 1, phi 2, and this we'll call phi 3. So phi 0 minus phi 3. So I'm using a special notation here. Just bear with me. It's quite interesting. Is equal to 100 volts. We know that. It's phi 0 minus phi 3 because phi 0 is 100, phi 3 is, all right. Now I'm very artificially, I'm introducing phi 1. I'm doing phi 0 minus phi 1 plus phi 1 minus phi 3. So all I did is I did minus phi 1 plus phi 1 equal to 100 volts. This is something you can do when you're doing complicated circuits. So I'm putting this in brackets, and phi 0 minus phi 1 is the voltage on the first resistor. So let's label this I1. So this is I1 R1 plus I1 R2. And that's equal to 100 volts. So I1, so it's 1000 I1 plus 3000 I1 is equal to 100. So I1 is 1 divided by 4, 0.25 amps. So the current here is 0.25 amps. I'm doing the same thing again. Phi 0 minus phi 3 is 100 volts. And I'm introducing phi 2. Phi 0 minus phi 2 plus phi 2 minus phi 3 is equal to 100. Putting this in brackets. And phi 0 minus phi 2 is the potential difference across this. So this is I2 R2 plus I2 R4 equals 100. So I2, so that's 2000 ohms times I2 plus 4000 ohms times I2. You might be right. 100 divided by 4000. Yes, 0.025. Apologies. That is 100. So I2, so 100 divided by 6,000. 6,000. 1/60th, or yeah, well, let's leave it as 1/60th amps. So, and then we can say phi 1, phi 0 minus phi 1 is equal to I1 times 1000 times R1. And because we know phi 0, so we can work out that phi 1 is phi 0 minus 1000 times 0.025. And we can see that this is phi 1, it's 100 minus 25, so it's 75 volts. Phi 2 minus phi 0 is I2 R2. So phi 2 minus 100 is equal to 1/60th times 2000. So phi 2 is what's that? 1/60th times 2000. 33.3 volts. In other words, oh, of course, it's phi 0 minus phi 2. Phi 0, so it's 100 minus phi 2. Minus phi 2. So phi 2 is 30. So it's 100 minus answer is 66. 66.7 volts. So in other words, phi 1 is greater than phi 2. So current cannot flow from right to left. Current cannot flow from right to left. Therefore, you have case 2 is not applicable. Are you still on board with me? Are you following through? How well do you understand what I did? On a scale of 0 to 10, please. All right. So what I've done is I have established that if we had this circuit, then phi 2 would be greater than, so phi 1 would be greater than phi 2. In this circuit, so adding a diode here if you add a diode, current will flow from phi1 to phi2, because phi1 is 75 volts. So this is 100 volts. This is 75 volts. This is 0 volts. And this is 66 volts. So if you add a wire here, the current will flow right, but not left. Therefore, this is not applicable. The current is not flowing right to left. The current flowing is left to right. Therefore, we do have a wire here, and it is equivalent to us not having a diode at all. So effectively, what I'm saying is that this circuit can be replaced by this circuit, and it will perform in exactly the same way. So let's go for it. So what we need to do is do Kirchhoff's laws. So let's say this is I1. This is I2. This is I1 minus I2. This is let's call this I0. I0, this is I0 minus I1. And this would be I0 minus I1 plus I1 minus I2. In other words, I0 cancels, so this is I0 minus I2. And here we're back to I0. Okay. So now we choose sort of a loop. We go from here to here. We won't use the loops here because, well, technically there aren't any loops, but we can use the potential rule. So label this point as phi0. Label this point as phi3. So phi0 minus phi3 is equal to 100 volts still. So phi0 minus phi1 plus phi1 minus phi3, using the same method. And we can say that this is phi0 minus phi1. This is I1 times 1000 plus I2 times 3000 equals 100. What do we need to find? We need to find I1 minus I2, of course. Then we do phi0 minus phi3, and that's plus phi4. And that's equal to 100. We plug in phi2, so phi0 minus phi2 plus phi2 minus phi3 equals 100. And here we do a very similar thing. We say that this is I0 minus I1 multiplied by 2000 plus I0 minus I2 multiplied by 4,000 equals 100. So let's have a look. We have 2 equations, but we only have but we have 3 unknowns. Okay. No, we can also use the fact that phi1 is equal to phi2 because they have to have the same, because they're connected by a wire. Along a wire, so basically phi0 minus phi1 has to equal to phi0 minus phi2. In other words, I1 times 1,000 is equal to I0 minus I1 times 2,000. And that's our third equation. So we have 3 unknowns and 3 equations. We can solve it. I'll change color. Make it a little bit neat. So we have 1, 2, and 3 equations. So from the third equation, I have 1,000 I1 equals, so 3,000 I1 is equal to 2,000 I0. So I1 is 2/3 of I0. That's useful. What else can we do? We can say that I2, well, we can go here. So from the first equation, I2 is equal to 100 minus 1,000 I1, 1,000 I1 divided by 3,000. In other words, I2 is 100 minus 1,000 I1, so that's 2,000 I0 divided by 3, divided by 3,000. That's 3,000. It's a bit stressful here. So that's 300 minus 2,000 I0 divided by 9,000. 9,000. And now we just need to plug that in. I think this will take a long time. So I'm going to cheat here. And I'm going to use my simulation. Let's double check that we are, well, at least are on the right track. So FET circuits. Oh. Yeah. Doesn't like that. Okay. And the batteries, it's an ordinary Is it though? An ordinary battery. 100 volts. Yeah. So we need to create a potential difference. So this is plus 100 and this is 0. So current flows. So this is 1,000. This is 2,000. This is 3,000. And this is 4,000. Okay. Let's look at the current. So here the current is 0.04. Not very informative. 0.03, 0.01. So we got this. So this is 3 times that. This is 3 to 2. Remember, so the ratio of the currents is 3 to 2, 0.02, 0.01. And let's measure some voltages. So first of all, the voltage from bottom to top is 100 volts, as it should be. And now the interesting thing, if you measure the voltage across this wire, it's 0. And it has to be 0 because there's no potential difference across this. If I remove this wire, the potential difference becomes 8.33, as it was here. 75 and 66.7. The potential difference is 8.33. But we do have the wire, and the wire changes that voltage to 0 because the wire effectively equals the potential at 2 different points. Right, it balances out like instantly. The moment you connect some 2 places with a wire, the potential becomes 0. That's why when you connect the terminals of a battery with a wire, you have a short circuit. You know, the potential difference across the battery, well, it's not 0. It's not 0 because the wires are not perfect. The wires have resistance. So of course, if you measure the potential difference must be, well, it just breaks down. It doesn't give you 100 volts. But real wires have resistance. Therefore, the voltage is 100. The voltage is 100 volts because the wires have resistance. Okay. So breaking this down. Right. So I hope that makes more sense. So this is 0.04. Yeah. So the current here something's going on. Why is it 0? 0.1 here, 0.3 here, 0.2 here. So 0.1 must be 0.1 here. Interesting. 0.4. I think you agree that if you have 0.3 here, 0.2 here, it must be 0.1 here. I don't know why it shows 0. Something's wrong with the system, but 0.1. Solve. All you need to do is solve the simultaneous equations, which I'm a bit too lazy to do at this point. You need to solve for the current, and you should have the answer of 0.01. Oops. I think it's just a rounding. Oh, of course, because the resistances are so large that the circuit construction kit, it just rounds. So probably the answer is not 0.01, but something along the lines of 0.04, which rounds to 0.0. Anyways, let's move on. Let's do this one. The next problem 5. It's not on Kirchhoff's laws, and then we can go back to problem 4 if we have time. Find the resistance between A and B in the infinite chain of resistors. It's a very similar problem to the one that we did last week. And so what you need to do is this one is R over 2. Then you have NR. Okay. R. So yeah, it's a little bit more sophisticated than the previous one. So what we need to do is say, okay, the resistance of this chain. Okay, the resistance of this chain, let's call it R1. Let's call it R1. And because it's an infinite chain, then adding another resistor to the left of it will not make a difference. So we are looking at this chain separately. The chat. Looking at this chain. So we have this and R. Etc. We can say that this chain, this whole chain, is equivalent. This whole thing is equivalent to just having one resistor of R1. And as I said, because it's an infinite chain, then adding another couple of resistors on the left will not change R1. In other words, if you take the R1 and you add NR and you add R here, this will still be equivalent to R1. So let's find the resistance of this combination. So that is going to be, so the resistance of two resistors in parallel. You should know resistance of two the total resistance of two resistors in parallel is R1, R2 divided by R1 plus R2. It's a short formula. It comes from the formula for parallel connection resistors. So in this case, these two resistors in total will give you NR times R1 divided by NR plus R1. Together with this resistor, it will be plus this one, plus R, and the total has to equal to R1. We can solve this equation for R1. So NR R1 plus NR squared plus R1. So what I did, I multiplied by NR plus R1. That's equal to NR R1 plus R1 squared. Okay. So R1 squared. Oh, this cancels out neatly. Minus R1 minus NR squared equals 0. So I need to solve the quadratic equation. Can I short circuit here? Can I make my life easier? Well, completing the square makes it easier. R squared minus R1 plus R squared over 4 minus R squared over 4 minus NR squared. So now I can combine these two. R1 minus R over 2 is equal to square root of R squared over 4 minus NR squared. So R1 is equal to R over 2 plus quarter minus N. Y minus plus. It's equal to 0. It's plus. Plus. Okay. So it can't be minus because then the answer would be negative. So it can't be minus. So I'm completing the square. I'm completing the square here. And it's plus or minus here, but it can't be minus because then the answer would be negative. Therefore, R1 is R over 2 plus R. So that's R over 2 plus R square root 1 plus 4N over 2, which is R over 2, open bracket, 1 plus square root of 1 plus 4N. All right, hope you're not overwhelmed with this. So this is R1. I mean, you know how to solve quadratic equations. If you are confused here, just go through it again and make sure that you have solved. It's a quadratic equation that's solved for R. Solve for R1. I don't want to get in too much detail on how I solve the quadratic equation. Okay, if I lost you at some point, just go over it again. Solve for R1. And it is a really good practice to solve quadratic equations like this. So we found R1, and all we need to do now is to find the total combination. So now we have R1, which we have found, R1. Then we have NR, and we have R over 2. R over 2. Therefore, this combination yields NR R1 over NR plus R1 plus R over 2 plus R over 2. It seems like I can see a shortcut here. So here, if you compare these two expressions, you can see that NR1 and R1, it's So from here, you have nr r1 over nr plus r1 is r1 minus r. So I plug that into here. So r1 minus r plus r over 2. In other words, it's r1 minus r over 2. So our total is r1 minus r over 2. And r1 we already have. It's r over 2 plus r over 2 square root 1 plus 4n minus r over 2. It's beautifully cancels out, and the answer is r over 2 square root 1 plus 4n. Actually, it's a very satisfying answer. Okay. Find resistance R small if both combinations have the same overall resistance. Well, I'd say it's a more or less a math problem, and it's actually the same. As you can see, it's the same thing. It's the same problem. Remember, an infinite chain, and you're adding another pair of resistors on the left. So I'll leave this one to you. Well, just here you can say that this combination is here. So if we label this as R1, and this is R1, it's the same process. We have 2R R1 over 2R plus R1 plus R is equal to R1, and you just solve for R1. Solve for R1. Do you see this? Do you see how to do this? Do you think you can do this problem on your own? Yes or no? Okay, another question. If I do this, do you still think you can solve it? Okay. I'll leave this. So this combination is R1. And here the combination is also R1. This is also R1. So now we have R1 in parallel with 2R. So that is, so the resistance of these two, using the formula R1, R2 divided by R1 plus R2. So the total, so that's going to be R1 multiplied by 2R divided by R1 plus 2R. So that's just using the formula for the parallel combination, because this R1 is in parallel to this one. And now this one is in series with these resistors. So all we need to do is R1 times 2R, R1 plus 2R, plus R, plus this R. And that is equal to R1. And this is where this equation comes from. So hopefully you get it now. All right. 57 volts, and this is 32 volts. So in this question, what you need to find is the potential difference between A and B if you know that the ratio of the internal resistances is 1.5. Now, what would happen to this circuit if the batteries were perfect? With no internal resistance. What would happen? What would if batteries had no internal resistance? This is an interesting discussion. So let's go. Let's get sidetracked a little bit. Imagine you have two batteries in parallel, and you're trying to power a light bulb. And imagine that the one battery is new and it's 1.5 volts. And one battery is old, which is let's say it's 1.4 volts. Like, batteries don't really lose voltage as they get old, only ever so slightly. And imagine they had no internal resistance. So what would happen? What would the behavior of this circuit be? What do you think would happen? What's the voltage on the battery? What's the voltage on the lamp? Voltage on the lamp. Edith, not really. It's not 2.9 because it can't, they don't add up. These batteries push in the same direction. So if you say that the potential phi and potential here, you can say phi1 minus phi2 must be equal to 1.5 volts. On the other hand, phi1 minus phi2 must equal to the voltage on the lamp. So the voltage on the lamp must be 1.5 volts because it's parallel to this battery. Until you realize that it's also parallel to the other battery, which is 1.4. And that's a problem. Okay, you cannot have this. It's a contradiction. You're contradicting Kirchhoff's second law. So you have the lamp is in parallel to the battery, The lamp is parallel to this. Well, there's no contradiction if you stop assuming that these are perfect batteries, because batteries are not perfect. They cannot be perfect. So what would happen if the batteries were perfect? Let's have a look. And I like this example. So battery. So this is 1.5. And this is 1.5. I'll just keep it 1.5 for now. 2 batteries and a light bulb. I'll reduce the resistance of the light bulb so that you have that it's reasonably bright. So you can see a perfectly good circuit. Both batteries are powering the light bulb. Nobody's hurt. Everything's good. Okay. If you measure the voltage, as it should be, the voltage is 1.5 volts. The voltage here is 1.5 volts. And the voltage on the battery, surprise, surprise, is 1.5 volts. So what's your prediction? What happens when I change this to 1.4? If I change this to 1.4, what's the voltage going to be? What's going to happen in the circuit? Well, let's have a look. I'm changing this voltage to 1.4. You have a short circuit. All I did is I changed it to 1.4. Now, the voltage, don't look at the voltage because the voltage doesn't really matter. What's happening here is a massive current flowing. So why is there a massive current? Well, because there's zero resistance, and there's a potential difference of the total potential difference in this circuit is 0.1. So if you have 2 batteries in parallel, they work against each other. And if they are, so the resistance of the circuit is 0. And if this is 1.5 and this is 1.5, the total EMF total is 0 volts, because 1.5 minus 1.5, they're pushing against each other. But suddenly, if this becomes 1.4, now the EMF total is 0.1 volts, the resistance is 0 ohms, and the current is equal to EMF divided by resistance, which is 0.1 divided by 0, which is infinity. You have an infinite current flowing through this combination. This is the reason why in every single device it says do not use new batteries with old batteries, because things like this happen. To be fair, in most devices, you have batteries which are in series and not in parallel, and this is not an issue when batteries are in series. because in series, it's perfectly okay to have two different voltage batteries. Well, ish. Okay, you have 1.5 and 1.4. It works perfectly fine. The reason why you don't put new and old batteries in series is that when one battery runs out, the second starts pushing current through that battery, and that can cause batteries to leak. All right, so if you connect different voltage batteries in parallel, that's a short circuit. If you connect different voltage batteries in series, new and old batteries in series, when one runs out, it runs out of chemicals that produce the potential difference. So the other battery starts pushing current through the battery, and that can cause leakage. So that's some interesting facts about batteries. Batteries do tend to leak, and they do tend to spoil things. I'm sure you're aware of that. If you're not, you're very lucky. Okay, so getting back to this problem. If batteries had no internal resistance, that would be a short circuit. So one battery would be pushing current in an infinite loop, resistance 0. The total EMF total for this circuit is 57 minus 32, which is 57 minus 32, which is what? 29? What? 20, 25 volts. The total EMF. Any questions? Any questions here at this point? But the batteries have internal resistance, and the ratio is 1.5. So we can say that R1 is 3R, and R2 is 2R, just for simplicity. So we don't so we don't have to deal with the ratio itself. So R1 is 3R, and R2 is 2R. And so we know that the total EMF is 25 volts. So the total resistance, resistance total is 5R. So the current is equal to EMF total divided by R total. And that's 25 divided by 5R, which is 5 over R. Okay. So there's a current flowing this way, current. So we have phi A and phi B. And we can write that phi A minus phi B, potential difference across, or the terminal, that's the terminal voltage, is the terminal voltage of 1V1, which is equal to EMF1 minus current times the internal resistance, R1. So phi A minus phi B is equal to 57 minus the current, which is 5 over R, multiplied by 3R. So R cancels. So it's 57 minus 15, which is 42 volts. And that's the answer. You can double check that the same applies for the second battery. It's just for the second battery, you have to take current as negative, because current goes in the opposite direction. So this is plus, this is minus, the current is flowing this way. So instead of minus, it's going to be plus. Right, so we have some time left. Which problem should we do? Let me see if I have any problems. This is a nice. Okay, well, let's practice. Let's practice Kirchhoff's laws again. Okay. Problem 4. Find the potential difference between A and B in the diagram below. So basically, what they're asking is if we connect a voltmeter here, what will the voltmeter show? Right. What will the voltmeter show? So let's have a look. Well, let's draw some currents. We don't know the direction of the currents, but there's a three EMF here. So I'm assuming the current will flow this way, the current will flow this way, and the current will flow this way. I'll call this I1, I'll call this I2, and I'll call this I2 I3. I3. Yes, that's fine. You can call it I3. So the first thing we know that is I1 is equal to I2 plus I3. That's the first equation. Okay, now we choose a loop. Let's choose this loop. So if the current flows this way, so this is plus, this is minus, this is plus, this is minus, this is plus, this is minus. And we need to assume that there are resistors here. This is a resistor of resistance R, and it has plus here and minus here. So plus because the current flows from plus to minus through a resistor. Through the plus and minus indicate the potential difference across the resistor. And here we have another resistor, which is 3R. And the current is flowing right to left. So this is plus, this is minus. And here we have another resistor here, which is 2R. And the current is flowing from left to right. So this is plus, this is minus. Now, we don't know the actual direction of the current, but that doesn't matter. It's okay. We can still solve it. If we get a negative value for the current, that means that we were wrong. So what we need to find is find I1, I2, and I3. So take a loop. So let's choose a green loop. And this is our green loop. And we'll go around the green loop clockwise. So green loop. Going clockwise. If we go from plus to minus, it's a plus. So it's plus EMF. It's a plus the voltage on here. It's going from plus to minus. So plus I1R. It's the plus the voltage on this resistor. Because we're going from plus to minus. Here we go from plus to minus. So it's plus so that's I1R plus I3 times 3R. And now through the battery, we go from minus to plus. Therefore, we go minus 3 EMF. And thus, that must equal to 0. Now, let's take another loop. Let's take loop, let's take an orange loop and go through this loop. And we're going through this loop clockwise. Again, it doesn't really matter which way you go. So orange loop. So first, we start here. We encounter the first thing that we encounter is the resistor, and we're going from minus to plus, so it's minus I1R. Then we go through the battery again from minus to plus, so minus EMF. Then we go through this battery, so from plus to minus, so plus 2 EMF. And then we go through the resistor from minus to plus, there's going to be minus 2R I2. And that's equal to 0, of course. Now, it looks like we have 3 equations and 3 unknowns. Yes. 3 equations, 3 unknowns. I think we're ready to solve it. So I could have taken another loop, but it looks like I won't need it. So from here, I can say that so the first equation is I1 equals to I2 plus I3. So here I have I1 plus 3I3 is equal to 2 EMF divided by R. Okay. It looks like I haven't made an error here. So from here, I can say that I1 plus 2I2 is equal to EMF over R. Okay. So from here, I can say that I3 is equal to 2 EMF over 3R minus I1 over 3. And from here, I can say that I2 is EMF over 2R minus I1 over 2. And I can plug that in. So look, just let's make a step back. Making a step back, you can see that this is the end of physics. I like to say this phrase. This is where physics ends and maths begins. So everything to the left of the purple line is physics, everything to the right of it is maths. So what you've done, you've written out 3 equations with 3 unknowns, and now you just solve it. So solving it is just a mechanical thing, right? It's a thing that trained mathematicians do. Okay. You don't even need to know the meaning of I1, of EMF, and etc., etc., etc. It's just developing your math skills. Here, using Kirchhoff's laws. So using the Kirchhoff's first law and using the Kirchhoff's second law. I'm sure you can solve this. I will solve it to the end. So I1 is equal to I2, which is EMF over 2R minus I1 over 2 plus 2 EMF over 3R minus I1 over 3. So I over 2 plus I over 3, that's 5I over 6. So that is 11I1 over 6. If I'm not mistaken. I3 plus 2, 5 over 6 plus 6, 11. And 11I over 6 is equal to 3 plus 4, 7 EMF over 6R. 6 cancels, and I1 is equal to 7 EMF over 11R. What do we need? We need between A and B. So we need I2. We need to know I2 to find the voltage between. Or do we? Oh no, it's fine. We need to find the voltage between A and B. So we do phi A minus phi B. That's what we need to find. Phi A minus phi B is equal to, because if you connect these, it is the same as if you were connecting across this, is equal to phi A. Let's put a dot here and let's call it C. It's phi A minus phi C plus phi C minus phi B. So I'm using this trick, and that's equal to phi A minus phi C. So this is A as well. Yes, because potential along the Y does not change. So A, you're going from A to C and going from minus to plus. So it's minus I1R. And here you go from C to B and you go from minus to plus. So minus EMF. So you just plug that in. Plug that in. So that's 7 EMF minus 7 EMF over 11 R times R minus EMF, which is minus 7 EMF over 11 minus EMF, which is 11 plus 7, 18, minus 18 EMF over 11, and that's the answer. Okay. Right, a question. Do you think you would be able to solve this problem from scratch? If I give you the same problem. Yes or no? Yes, with time. Anyone else? Okay. Okay. Well, most of the problems in the assignment are not as difficult. But please go back if you haven't seen the previous webinar. Please go back to see how I deal with Kirchhoff's laws, how I do Kirchhoff's laws. So it's about putting these pluses and minuses. So the plus goes on the side of the component that has higher potential. Higher potential along higher voltage. So pluses and minuses. So Kirchhoff's using Kirchhoff's laws. So if you have a component, I don't know, lamp. If you go, if the current, let's say the current goes from left to right. So the current flows from left to right. That means here, you have high potential here, low potential here, because current through a resistor always flows from high potential to low potential. Battery always has high potential on the plus side and low potential on the minus side. The lamp is the same as the resistor. It has high potential where current enters and low potential where current comes out. So if you rate this voltage on the resistor, the EMF, and voltage on the lamp, if you go from left to right through the loop, you will go plus VR, plus EMF, and plus VL. And if this was a closed loop, that would be equal to 0. If it's not a closed loop, then it's just potential across the ends. So the phi A, phi B, that's equal to the potential difference across the ends, phi A minus phi B. Now let's assume that the current flows the opposite way. We have, this would be plus, this would be minus, because current goes from plus to minus. EMF would be plus, minus, and this would be plus and minus. So that's voltage on the resistor, that's EMF, and this is voltage on the lamp. And again, this is A, and this is B. So the potential difference across A and B, we're going from left to right. So we just go literally like mentally walking along the wire. So it's going to be minus voltage on the resistor, plus voltage on the battery, minus voltage on the lamp, and that is equal to phi A minus phi B. Right. The voltage on the resistor is, of course, IR minus IR plus EMF minus IR for the lamp. And this is the resistance of the resistor, this is the resistance of the lamp. Right. Does that make sense? Does this make sense to you how to deal with Kirchhoff's laws? Do you understand? On a scale of 0 to 10, please. If you have a question, do ask. I'm happy to explain. And this is how you use Kirchhoff's laws. So if you have a closed loop, that would be 0. Basically, if you have a wire connecting A and B, that means that phi A minus phi B is 0. Therefore, this would be 0. But if they're not connected by a wire, it's not 0. So Kirchhoff's second law says across any closed loop, the total potential difference is 0, which is duh, because the potential at the start is equal to the potential at the end. Yes, that is true. It has to be. It has to be. So, but when you get your head around this way of looking at circuits, Kirchhoff's laws become obvious to you. And yes. And looking at potentials. So I hope this was useful. I'll leave you here. Enjoy the assignment. Enjoy the extra week. Enjoy Easter break. I see